Hi, so today we're going to be talking about sets and set notation. Before we jump into any examples, I think it's important to talk about the basics of sets. When you say set, you typically think of something like a group. It's a collection of objects. So a set of English letters would be 26, and there's many ways of defining and describing a set. So one of those ways is the roster method. And that would be when we list all of the objects in a set. So if we say we have a set that has all of the numbers between 1 through 5, all of the integers between 1 and 5, if we wanted to list that in the roster method, it'd be 1, 2, 3, 4, 5, and that would be it in the roster method. When we have sets, the orders of the list, like of the items in the list, it does not matter. So if you had 1, 3, 2, 5, 4, these two sets are equal. When we have two sets that have the same number of elements, that means that they are equivalent, and that's usually shown like this. So if you had a set of numbers that was like 1, 2, 7, and you had a set of numbers that was like 3, 42, and 1, these two sets are not equal, but they are equivalent because they have the same number of elements in the set. There's also a concept called the cardinal number. Oops. And that is basically how many elements we have in our set. So if we had the set of the alphabet, A through Z, there would be 26. And the way to denote that is the name of our set with these straight brackets, and then would be like equal 26. Whoops. Don't confuse this with absolute value. There are some, I have an example problem later on where there's one that has both this and absolute value, and we'll figure out how to tell those apart. The next idea is set builder notation. So when we have a set, a lot of times it's really hard to list all of the elements, or impossible to list all of the elements of a set, especially when it goes on to infinity. So a way to handle that while still describing the set is to use set builder notation. We describe the rules that define our elements instead of all of them, like all of them individually. So for instance, if we had, if we said that we wanted, we had a set that was a set P, and we wanted that set to have all integers, which is like -1, 0, 1, ... all integers. It's impossible to write all of the integers. There's infinity both ways, both negative and positive. So a way to handle that would be using set notation. So n, usually we say n, but sometimes it's x or whatever you need. N, and then this line here says such that n is an integer, which can also be written as this funky Z, right there. So you typically, see the set name, and then the bracket, and the n, such that n, and then the conditions, the criteria for n. Now, sets can be empty. There are sets with no numbers. This can be called like a null set, and you can write this either with doing empty brackets like this, like A is equal to empty brackets, or A is equal to, I don't remember the name, I think it's like subnot or something like that. I don't remember. But it's this little funky 0 with a line through it. Universal sets have a specific meaning depending on the context. So like all of the letters of the alphabet, or all of the plants that grow in the state of Utah, like universal sets would have all of them together. And a lot of times we'll be dealing with a subset of the universal set. So like if we have our alphabet example, let's say set A is equal to cat, well, C, comma, A, comma, T. It would be cat, this subset here, this set would be a subset of the universal set of the alphabet, which is A, B, C, D, E, F, G, dot, dot, dot. So for like an example, well, we have example problems. We'll just hop into the examples now. Sorry, I was thinking. So this one is asking for A prime, which is, well, it's asking for the cardinal number since it has these brackets here. But we'll do it as if it was asking for both the cardinal number and like roster. So we can see in set A, we have H, so we can cross out H in this one. Y, cross out Y. D, R, O, P, L, A, N, E, S. And so our A prime, the cardinal number of our new set, when you see this prime thing, this little 1, that means that it's asking for the rest of the set, of the universal set that doesn't include our original one. So in this case, it'd be B, C, F, G, I, J, K, M, Q, T, U, V, W, X, Z. And then our cardinal number would be if we counted that, which is 15. So the answer for this one would be 15. If it wasn't asking for the cardinal set, you would just take this and you would add brackets around it. This one is telling us that we want to use the given sets to answer the question, is P equal to Q? Why or why not? So this says July, October, November, December, May, and April. And this one says October, so we have October similar. This one says June, but our P does not have June. This one has November, they both have November, they both have May, and they both have April. But these sets differ on July, December, June, and September. So they are not equal. They are equivalent, but they are not equal. So our answer would be no, because the sets contain different elements. If it was asking whether P is this little squiggly line equivalent to Q, then it would be yes, because they have the same number of elements. Yeah. This example is asking us to find the cardinal number of the set, and this one is using set notation. So we have G is an element of N, which stands for natural. So G is an element, well, this is G, such that G is an element, this little weird E thing means, is an element of all natural numbers, and G is odd, and G, the absolute value of G, has to be less than 6. So for this one, we know that, we have our natural numbers. So one moment. So here are the natural numbers, 1, 2, 3, 4, 5, that is less than 6. Natural numbers do not start at 0. We know that it's odd, so we can get rid of our even numbers. So 2 and 4. So we have 1, 3, and 5, so our cardinal number is going to be 3. If it was asking for integers instead of natural numbers, in that case we would have -5, -3, -1, 1, 3, and 5, because we know that the absolute value has to be less than 6. So if we had -7, the absolute value of -7 is just +7. And that is greater than 6. So this one is asking us to write this set using the roster method. So set A, so we have our bracket, is a set of positive 2-digit numbers greater than 39 and that are divisible by 5. So we can do N is such that N is an element of, we'll just do integers, which is this funky Z, and then comma, we know that it's going to be n is greater than 5. Oh, wait, sorry, greater than 39. Actually, if we do this, if we do 100 is greater than n, and n is, oh, sorry, sometimes with these it's hard to get it in the right order. Okay, I see. I misread. We're using the roster method. We are not using the set builder notation. So, in this case, we know that 40 is divisible by 5, 45, 50, 60, oh wait, sorry, 55, 60, 65. Oh, and we want odd numbers, so 40 and 50 and 60 aren't needed, so 75, 85, and then 95. This would be our answer. Sorry for the confusion. That's why I think that reading the question is the best thing that you can do. But yeah, if you have any questions, please let me know. And yeah, see ya.